All right, there have been a few questions about some of these mechanisms and figuring out the rate law expression from the mechanisms, especially when it comes to things like the rate determining step and how to work with intermediates. So I've chosen 3 questions on this assignment, number 10, number 12, and number 14, that I just want to work through and give you a little guidance if you feel like you're struggling on working those sorts of questions out. These are 3 that were a little more tricky, perhaps, but also ones that I've seen people making mistakes on here and there, so I wanted to kind of address those collectively. Hopefully this will help you out. For number 10, want to find that slow step. Remember that the rate determining step, a slow step, should be the one that you sort of work from as far as writing your rate law expression. It helps, though, I think, in most cases, to have the overall reaction in place as well. You don't actually have to have the overall reaction here in order to write the rate law expression, but it helps because it gives you sort of your options as far as writing that rate law expression properly. So to do that, I'm just going to kind of work through and figure out what will the overall reaction be. And of course, that means canceling out intermediates, and that means canceling out any catalysts that we see. Well, we have chlorine here as an intermediate because 2 chlorine atoms or radicals are being formed in that first step, and then they're being used in step 2 and step 3. And then in addition to that, we have CCl3 formed as an intermediate in step 2 and then used up in step 4, or step 3 rather. And then that's it. The rest of it remains. So our overall reaction is Cl2 plus CHCl3 makes CCl4 and HCl. So there's our overall reaction. I'm just going to take these back out again so we can see things. But why that's helpful is because it reminds us that as we write our rate law expression, the only compounds or molecules, substances, that can appear in the rate law expression are reactants in the overall reaction equation that we see here. So chlorine, Cl2, and CHCl3 are the only ones that are allowed to be part of the rate law expression when it comes to writing it. So we know that rate law expressions follow the format of rate equals K times, and then each substance's concentration to raised to its appropriate order, as determined by the reaction and the mechanisms that we've got here in place. So as we work on number 10, we do take that slow step, and the basic idea is for the slow step, take the reactants from the slow step, right, and list them in the rate law expression. So for the slow rate determining step, I have CHCl3, and I have 1 mole of it, so I'll make that first order, and I have Cl, and I have 1 mole of that in my equation, so I'll make that first order. Now if I look at that, CHCl3 is one of my reactants from the overall reaction equation, so CHCl3 can be in the rate law expression just fine, no problem with that. However, chlorine, Cl, the atom here, cannot be in the rate law expression because it's not in the overall reaction equation here as a reactant. And the reason that that's the case is, as we noted earlier, right, it's because it's an intermediate. It's formed during step 2, and it's used up in it's formed in step 1, and it's used in step 2 and again in step 3. So we can't use Cl in the rate law expression. So what we have to do there, instead of using Cl, is we sort of have to trace its history. What were the reactants that led to the forming of that chlorine in an earlier step, right? Is the idea. So we kind of trace its ancestry. And so for that chlorine, where did that chlorine come from? It's an intermediate, we can see, but where did it come from? Well, it came from step 1. Right? It came from like right here. And so chlorine in step 1 was formed by the reaction, in this case the breakdown or decomposition of Cl2. And so we want to include Cl2 and substitute that in place of the Cl. So this intermediate that was part of our slow rate determining step came from a previous reaction. It was the product of a previous reaction, and we have to trace our way back sort of to the beginning of that reaction and substitute in its place the reactant that formed the intermediate. And Cl2 is a great choice because Cl2 is, well, it's correct, but it's also part of the overall reaction equation. So Cl2 is, so to speak, allowed to be in the rate law expression because it's a reactant in the overall reaction. It's not an intermediate. It can be part of the rate law expression. However, here's the thing. To make, in my first reaction here, I'm just going to kind of erase some of this again because it gets a little bit cluttered if I have too much business going on the outside here. To make 1 chlorine, right, which is what we need for this reaction here, to make 1 chlorine that we need in our slow rate determining step, I only used, if we're getting real honest, I only used half of that Cl2 to get there, right? Because it made one Cl and another one Cl, but we only need one of those two chlorine atoms that are being made. And so to make the chlorine that we need here in our rate law expression that we're going to substitute out, to make that, it takes half of a mole of Cl2 to make a Cl atom. It makes sense. It takes half a mole of Cl2 to make a regular Cl atom. And so what's going to go in place of Cl in my rate law expression is Cl2, but to the half order, or to the 1/2 power. So my overall final result here then is rate equals K times CHCl3. That one's been okay from the start because it's a reactant in the overall reaction equation. And now we're going to substitute in here Cl2 to the 1/2 power. That's our rate law expression for number 10. It includes reactants from the slow step that are also reactants in the overall reaction, that is CHCl3. And then it includes the reactants that led to the formation of any intermediates that are part of the slow rate determining step. And Cl2 is a reactant that led to the formation of the chlorine radical, which was a reactant in the slow rate determining step. And again, remember, in the end, when you come up with your final official answer for a rate law, whatever substances you put in that rate law expression, here we have CHCl3 rather, and then Cl2, have to be among the reactants in the overall reaction equation, and we see that they are. You don't have to include all of these necessarily in every example, in every reaction, but the only things that are okay to have in your rate law expression have to be from that list of reactants in the overall reaction equation that we see there, that we wrote before we got started too far. So hopefully that makes sense. Let's take a look at number 12. 12 has some similar sort of challenges, I guess I would say, to it, but we have to think through a few different options for mechanisms. And they ask us to decide which of these three mechanisms, A, B, and C, which would be a valid mechanism for the reaction if this is the rate law. So it's kind of doing what we just did, but in reverse. Instead of having to write the rate law, we have to examine the known rate law. It's been already determined, okay? And figure out which of these mechanisms, and there could be more than one of them, it's appropriate, which one of these mechanisms would give us that rate law. Well, let's start with the easy one. And most people who had a mistake on number 12, or would be likely to make a mistake on number 12, would recognize that mechanism B definitely works, because there's really only one step here, and so it doesn't say that that's the slow step, but when there's only one step, that's the rate determining step. There's no other slower one. It's got to be considered the one step that's going to determine the rate law, because every reaction has a rate law, whether it's one step or 3 steps or however many. So when there's only one step, then that's the one that gives it to us. So my rate law expression for that very simple one-step mechanism, if we can even call it a mechanism when there's one step. You can call it a mechanism, but it doesn't seem like one quite, would simply be the reactants, H2 and I2, each to the first power, to the first order. So yes, mechanism B fits the bill, because it's only got one step and it matches us. If we take a look at mechanism A, the slow step, right, will help us to write our rate law. The slow step's going to give us a rate law expression of rate equals K times the reactants from the slow step. And the reactants from the slow step in A are simply iodine, and one of them. Well, that's it. We don't have to include anything else because the slow step is the first step. That's definitely the easiest scenario. We don't have to look beyond the slow step at all when writing a rate law expression. And so when it comes down to mechanism A, there wouldn't be enough in there. It doesn't include the hydrogen that's part of the known experimentally determined rate law that was given to us in this problem. So no, mechanism A does not work. What I've written over here on the side would be its rate law, and it doesn't include the hydrogen that must be included. But let's take a look at C, which is definitely the trickiest sort of aspect of this. And part of it's because the slow step comes last. Whenever the slow step is later in the problem, like it is in this mechanism with C, that means you're going to have to do some backtracking or sort of some reverse engineering of this problem. And so what's that going to look like? If we take the slow step and we write the rate law expression for it, pardon me, screen slipped a little bit, I'd have rate equals K times H2I to the first power, since there's one of those in the expression, and then one iodine here, which is also just one of those in the expression. So one of each of those in a balanced equation, and we're done, except no. Problem. Both H2I and the iodine radical that we see here in the equation, both of these fellows here are intermediates. And so like we did on the previous question, number 10, we have to sort of trace back where did those intermediates come from. They're each intermediates that came from, well, they came from different reactions. Let's look at this iodine first. Okay, the second one. Let's look at the second one first. Where does this come from? This iodine is being formed in step 1, and it's being formed from an I2 molecule, right? So what's the ancestor of this intermediate? Well, I2 is. To make I, we had to break down an I2. And like in the previous question, to make a single a single iodine atom, which is all that step 3, our rate determining step, calls for, half of a mole of iodine I2 was necessary. We had to use half of this iodine I2 to make this I, and then the other half of it went into making this I. So 1/2 of it means we used a whole one, but half went to this production or this product, and the other half went to this product. It was sort of broken in half. Quite literally, it was broken down. And so we're going to substitute in place of the iodine right here in our rate law. We're going to substitute in half of an I2 molecule, or I2 raised to the 1/2 order, or 1/2 power. So that's going to get substituted in there. But what about H2I? H2I, again, is an intermediate. It's consumed here in the slow step after being made in the previous step, number 2. And so what went into making H2I? Well, if I look at H2I there, what went into making it? I've got iodine, one of them, and I've got H2, one of them, that went into making my H2I in step 2. Now, what's the overall reaction that we're looking at here? The overall reaction is what we see in step 1, where it's hydrogen H2 and iodine I2 making 2 HI molecules. And if we went through on mechanism C or on mechanism A and canceled things out, that's the overall reaction that we're looking for. So H2 and I2 can both be included in the rate law expression because they're reactants in the overall reaction, which again we kind of see right here. This is the overall reaction. So what? Well, it means that H2 is okay to include in the rate law expression, but this I, again, here at the very beginning, this I isn't. It's still considered an intermediate because it, like the iodine that we had a moment ago right here, this iodine is also an intermediate formed during the first reaction. 2 different I's were formed as products, 2 different iodine atoms were formed as products of the first step, and they both act as intermediates, later consumed in step 2 and in step 3. So what's the ancestor of this? What's the ancestor, rather, of this iodine atom, as we look at it here at the bottom of our work? Well, the ancestor of that is, oops, pardon me, is an iodine molecule. And like with the other one, we only need half of that to make it work. Half of the iodine in step 1 went into making the iodine that we see here. The other half of the iodine in step 1 went into making the iodine that we see here. And so we end up using half of an iodine twice, which means we've used a whole iodine, right? So let's put together all the pieces here that are acceptable to be included in our mechanism, or our rate law expression, pardon me. So hydrogen can be included because it's an overall reactant. Iodine can be included because it's an overall reactant. And iodine, again, here, I2, can be included because it's an overall reactant. So what does that give me? That gives me rate equals K times H2. And then I've got I2 to the half and another I2 to the half. And of course, we can put those last 2 terms together. By adding those powers together, our overall rate law expression becomes rate equals K times hydrogen to the 1 and iodine to the 1/2 plus 1/2, which is 1. And of course, our overall question said, this is the experimentally determined rate law, and sure enough, we've matched it up here. By doing quite a bit of ancestry sort of work, we've figured out that our intermediates, which were involved in that slow rate determining step, have their origin in hydrogen and iodine, and more specifically 1 mole of each. So, as kind of roundabout as it is, and you have to really, it's like digging into your family tree a little bit there, you have to keep going back until you hit rock bottom. And rock bottom is always going to be the reactants that we have in the overall reaction. Again, remember, the overall reaction here gives us sort of our word bank, gives us our options. These two species are the only things, pardon me, these two species are the only things that should be part of our rate law when we go to write our rate law expression. Right? So this is an option and this is an option, but none of those intermediates can be included. I should mention, I haven't before on this video, that catalysts can be included in the rate law expression because catalysts can be reactants going in and in some cases partially products coming out. It's not too common that you find a catalyst part of the rate law expression, but there are situations where a catalyst could actually be part of the rate law expression. I wouldn't say it's definitely not common, but it's not out of bounds. All right, let's take a look at number 14. 14 has three choices, kind of like we had with number 12. So we have to do the same sort of work. Let's see what we can rule out and what we can rule in. So I'll go through this one sort of maybe just a touch quicker so you don't get too terribly bored with it. But let's see if we can rule one out. Well, it's always easiest to start with one that's got a slow step early. In that slow step, like in our last problem, we have chlorine, Cl2, breaking down into something. In this case, we wouldn't say that it's breaking down into radicals, because we're getting a chlorine that's got a positive charge and a chlorine that's got a negative charge. But nonetheless, a single chlorine molecule, Cl2, is breaking down into two simpler parts. And so the rate law expression for that slow step then, our rate determining step, would be rate equals K times Cl2 to the first power, since that's what this equation calls for. And of course, we're trying to match it to this guy. That doesn't get the job done. So kind of like in the previous problem, A, nope, not going to fit the rate law that we know to be true. H2S wouldn't be part of the rate law using that first mechanism because it isn't introduced into the problem until a step that comes after the slow rate determining step. What about mechanism B? Mechanism B's pretty simple too. It's got a slow step right out of the gate, and in that slow step, chlorine, Cl2, and H2S, hydrogen sulfide, are both reactants, and it's a 1-to-1 ratio. So our rate law expression would be rate equals K times Cl2, 1, and H2S, 1. So sure enough, that one fits the rate law that they're wanting us to match it to up above. So yes, that's a valid mechanism for the rate law that was given. What about C? C is kind of like C in number 12. We have to do a little ancestry work. So again, for our slow step, our rate law expression, our rate law expression would be rate equals K times the reactants from mechanism C's slow step, which is that last step. So that's HS, and that's Cl. Now, neither HS nor Cl shows up in the overall reaction equation which starts this problem, right? We don't see HS or Cl as reactants in there, and so neither of them is allowed to be in the rate law expression. We got to trace their ancestors. Where does the HS come from? And where does the Cl come from? So, like in the last one, let's start with Cl. It turns out it has a little simpler story. Not that it really matters, but Cl is coming from step 1, and you can see that it's being made much like we've already seen. It's coming from Cl2, and it's consuming 1/2 of that Cl2 to make the Cl that we're interested in here, right? We'd need 1/2 of a molecule of Cl2 to make the Cl that's vital here in our rate law expression. So we'd substitute that in place of Cl. So we're going to have rate equals K times, well, let's save some space there, Cl2 to the 1/2. Okay. What else is going to get substituted in? What's going to come in for our HS? Well, HS is an intermediate. It was formed in step 2 and then used in our rate determining step 3. HS was formed in step 2, and it was formed from Cl, and it was formed from H2S, one of each. Well, H2S is okay, because H2S is part of my overall reaction, so H2S, that can be part of the rate law expression, just like this 1/2 of a Cl molecule could be from the other guy. So H2S can be in there. We can do that. But what about this Cl? This one has further ancestry needs. We got to look at this Cl, and where did he come from? Like the other Cl that we used here a moment ago in the overall expression, that second chlorine down the left there is coming from 1/2 of a unit of Cl2. half of a mole of Cl2 gives me this chlorine that's an ancestor to the HS. So we're kind of gone back almost to like a grandparent here, if you will. So that guy is part of the overall reaction equation up above, and so is approved to be part of the rate law expression. So I'm going to put that Cl2, whoops, I'm going to put that Cl2 in here as well, as expected. I'm sorry, I'm sliding some stuff around here, all wonky. As I sort of expected, I've boxed myself into a corner by writing things down early, so apologize. We're going to bring that other Cl2 in here and include it in my rate law expression. So the pieces here for H2S would, or rather HS, would be these guys, if we traced it back to its ancestors here and here. And then for the chlorine, for the Cl, it was part of my original expected rate law expression. That's this one here. So we've substituted in for those the things that you see over there on the right hand side, and like we did in the last time, we can kind of condense that down a bit. Rate equals K times H2S, and then Cl2 half of it and another Cl2 half. We can combine those together to have Cl2 to the first power, and so both of those would be to the first power, or the first order, and that rate law expression indeed matches the one we were trying to get it to match to back up here at the top of the problem. So yes, mechanism C would also be an effective or consistent mechanism for the rate law that we knew to be true. Generally speaking, I don't know that you'd have three mechanisms quite this significant on a short FRQ. I don't know that you'd have it on a fast exam. I don't know that you'd necessarily be expected to examine all three, but they could very well in a question give you one of these three mechanisms and ask if it's valid for the rate law that was given there at the top, and then ask you to explain why you know that, or why you know it is or isn't. And by explaining it, you could do the kind of work that we've done here. But you probably wouldn't necessarily get three mechanisms very often. Hopefully you could tackle it if you did, but to be able to examine a mechanism, find that slow rate determining step, and then make sure that whatever rate law expression you write for that slow step includes only reactants that were part of the overall reaction. And that's in this case, our Cl2 and our H2S. They're the only ones that can be included. Notice again, I mentioned earlier, if you look at the rate law expression for mechanism A here, it includes Cl2, which is from our overall reaction, but it doesn't include H2S. So just because a reactant is part of the overall reaction equation, as we see here highlighted, just because it's part of this equation doesn't mean it has to be in the rate law, but the reverse is true. If it's in the rate law, it has to be a reactant in this equation. So it's not a two-way street. They're not mutually inclusive kind of limitations that we've got there, if that makes sense to you. So there's a few. They got a couple others on here to try if you haven't worked through them. Hopefully that's helpful to you. If you have other questions about these, let me know. See me during office hours or something, and I'm happy to help you further if you still have questions. Thanks for watching. Have a great day. See you soon.